Hi there, folks. Hi there, folks. So this might be tad on the late side. Anyway, we'll get it out. We're going to be doing about alpha radiation today. Alpha radiation. Now, you should have done alpha, beta, and gamma radiation. That's kind of what we're going to do for the next 2 or 3 weeks. But we're going to be go a bit more in depth. First things first, alpha. The symbol for alpha is a fish, like that. It's actually a Greek letter from the Greek alphabet. If you can see it there, it's the first letter. There you go. Alpha, beta, and gamma. So basically it's the first type of radiation, then there was a second type of radiation, and then the third type. So they called it alpha, beta, and gamma. Alpha, beta, say it quickly. Alphabet, alpha, beta, alpha, beat. That's where the word alphabet came from. Anyway, we're going to look at alpha radiation now. Now, you should know that alpha radiation is like a helium nuclei. So it consists of 2 protons and 2 neutrons. So overall, we could say it has a relative mass of 4. And if we add up all the charges, we could say it has an overall charge of +2. It doesn't have any electrons, does it? It's just the nucleus. That's important. Doesn't have any electrons, just the nucleus. Okay? So how am I going to symbolise this? Well, I could write it in quite a few different ways. I could draw it like that. I could write it's 2, 4, He with a +2 there. Or I could write it as a 2, 4 alpha. Okay, these mean exactly the same thing. We can have a +2 there if we like. This +2 just means it's lost 2 electrons. Think of the helium atom, take away 2 electrons, it's got a charge of +2 now, and we've just left with the nucleus. If we were going to pen it, how many electrons has it got? How many neutrons has it got? How many protons has it got? Well, it's got 2 protons, no electrons, and 2 neutrons. So if you 2 and 2 plus together equals 4. And that 2 just goes up there. Okay, so we've talked about the relative mass, and we've talked about the relative charge as well. It has a charge of +2. Okay, and it is quite a big it's quite big, okay, compared to the beta radiation and the gamma radiation. Now, if I had an atom, and here is my atom, it's quite large. It consists of protons and neutrons, okay. Now, what will happen, there's all the protons and neutrons there, okay. Now, basically, this is too fat. Okay, the atom is too big, it's unstable. It releases that to become stable. Okay, it's got too much mass. Okay, you could think about it as it's sort of spread out too much over an area, and the force keeping it in, it's not as big as the force wanting to push it out. What pushes it out? Well, if you've got 2 protons next to each other, they're both positive, they're going to want to repel. So all these protons in here actually want to leave, but there's a force keeping them in. But that force doesn't work over a big long distance. So if the atom gets too big, it will want to get rid of some mass. And it gets rid of some mass by getting rid... Oh, my hands are just everywhere. Sorry. By getting rid of 2 protons and 2 neutrons. Okay, let's see what that looks like. Let's imagine let's get my periodic table up. Oh, my periodic table. Let's have a look at, let's look at uranium. Uranium is there. Let's just put it back on. Uranium. I wonder if I can zoom in. So there you go, uranium. Uranium 238 and has 92 protons. Okay, so that's unstable. It's too big. It's got too many protons. In fact, if it's got more protons, if the proton number is bigger than 82, then it needs to lose some mass. So what's going to happen is this is going to lose some mass, this one here. It's going to become something else. Just quickly, how many protons, how many neutrons? Protons, 92. Neutrons, 238 minus 92, 146. Okay, it's going to lose. It's going to lose 2 protons and 2 neutrons. Okay, so it's going to become. It's going to give something. Is going to be given off plus alpha. Now I know alpha has a proton of 2 and a neutron number of 2. So the proton number is now going to be, if it was 92, it lost 2, it's become 90. If it had 146 and it lost 2, it becomes 144 neutrons. What is a proton number of 90? It's not uranium anymore. Remember the isotopes. It's become thorium. And in doing so, the uranium, oh, I'm not pointing at the right thing, sorry. Uranium has become thorium and given off an alpha particle because its proton number was too big. Okay, you will find that all the elements after lead is there, all the elements after lead will actually give off alpha. You can see this by I think if you click on isotopes, is it? If you click on, say, polonium, all of the isotopes of polonium give off alpha. Look, they've got a yellow square around them, and it says yellow square there. Radon, the main one of isotope of radon is going to give off alpha as well. It's very strange in a way. Radon will give off alpha and can become polonium. Polonium will give off alpha and become lead. You could actually, we've got some at college when we go back. Yay! If, when, whatever. We've got some americium or americunium. It's going to give off 2 protons and 2 neutrons, and it's going to become neptunium. It's going to give off 2 protons and become protactinium. Okay, and that's how it happens. This is what alpha decay is. Okay, right, a new video coming up soon. Thank you very much. Bye.